distance from point charge. Okay, yeah. What will
Yes, sir.
electric field? Electric field we have to calculate and accordingly plot for the formula. Electric field against small r. Electric field due to point charge, and what being small r over here? Distance of the point where we want to calculate electric field due to point charge, distance of that point from point charge. Okay,
Yes, sir.
distance of that point from point charge. Vasudev,
Yes.
are you there? Unmute yourself.
Yes.
Vasudev, we were plotting for electric field versus small r. Kindly do the plotting. Electric field versus small r.
So
How
just
does
give me
electric field
1
vary?
second. I've set up my
Sure,
own
sure, sure.
recording mechanism. Skype
Sure.
happens to be pretty unreliable.
Mhm. We have the formula at our disposal which reads Q divided by 4 pi epsilon naught r square. I think you all can recollect. That is a formula for variation of electric field with small r. How does it vary vis-a-vis small r? So electric field is magnitude wise 1 by 4 pi epsilon naught Q divided by r square, where Q is the point charge and r is the distance from this point charge. How will it vary? Just to plot it, nothing much. It's a non-brainer, I would say. Non-starter, no-brainer out here. You can plot easily, keep electric field on your y-axis and r on your x-axis. Get me the plot.
So for a point charge.
Yeah. We have calculated as yet only for one configuration, right, dear? And that being point charge.
Yes.
There are many a configuration that we have to look for. And we have to look for two physical quantities. One is electric field, the other potential. We have as yet completed only with electric field, and that too due to only one configuration, it being point charge.
Towards the end of the class, would you mind touching upon electrostatic pressure? The topic came up in class.
Of course, will be. Electrostatic pressure is very important.
But in class, they dealt with it in a very hasty manner.
Of course, it will be dealt in a very haze and hanky-panky and wishy-washy as well. Why? Because it involves concept. Okay. Not about stress, formula of stress. We'll be taking questions. We'll be solving them as well. If you want to start right away, I don't have any comms. We can start it right away.
I'd rather take it in order.
We'll take it, no issues. Write down. Firstly, you get me the plot. What will be the plot like?
So a little bit scaled hyperbola, kind of.
It'll be a rectangular hyperbolic, right?
It won't exactly be a hyperbola because it's 1 by r square.
It'll parallel to y-axis when r is tending to 0, and parallel to r-axis when r is tending to infinity. Correct?
Yes.
That's the plot we'll be getting. Now, to address your query, what I'll do is I'll take a conductor. So let us write a conductor with uniform surface area sigma. A conductor with uniform surface area sigma is taken to study electric field that it will produce at its surface. Electric field that it will produce at its surface. Now, if I'm to take liberties on being certain formulae known to you, then can directly jump to stress and accordingly will make you understand what is electrostatic pressure. If we are to move in a hierarchy, then we need to see for different configuration, and they being primarily ring, shell, and sphere. These three configuration, and also later on in the beginning itself, we can deal with the other discrete system, which is dipole. Dipole 2 is a discrete system. So we have to study for discrete system first. Then we have to study for linear, which is linear charge density, and then go for surface. After that, volume. These are the configurations which we are looking forward for. I would suggest, if it's known to you, then I'll straight go to electrostatic pressure. If it's not known to you, then we should not be in a haze or should not rush through this topic. This is a very important topic. So your comfortability is what is priority for me. Are you comfortable with electric field due to different configurations, particularly shell, Vibha?
No, sir. No, sir.
Okay, what about you, Vasudev? Are you comfortable?
Yes, sir. They pretty much finished the chapter at Allen, so I mean, we got a test next week.
Okay, good enough. So what I'll do, we can go for a quick succession then. Whatever you are through, can we go for a quick succession?
Sure.
Vasudev? Okay. So we were dealing with electric field due to point charge, and we have drawn for the case. Can we also find electric field due to line charge? Find electric field due to infinitely long line charge. Find electric field due to infinitely long line charge. What will it be? Also find, I'm incorporating so that we can get in this class itself what you're looking for, which is pressure. Sigma square by twice epsilon naught is the pressure formula. How do we get it? We'll be throwing light on it and we'll be solving few questions as well. So line charge and dipole moment. Electric dipole. Line charge and dipole moment. Electric dipole. We call it dipole moment, but that is not the correct articulation. We should not nomenclature-wise mark it as dipole moment. So we are in the bracket emphasizing it being electric dipole. Right, dear?
Yes.
So I have taken for two cases. One is the line charge and the other is the discrete charge system. Why I say discrete? Because dipole comprises of two charges. And they have their identity, they are individual. So there we study for discrete charge system, and in line charge we study for continuous distribution. So what do we do for a line charge quickly if we have to look for? Tell me, what shall I do? How will I go about line charge here? This is my x-axis. This is my x-axis. This is my y-axis. My line charge is placed on y-axis. It is infinitely long line charge. Okay, got it? What we have to do, we have to find somewhere over here field due to it. This is point P. Where is it? Let's say it is at x 0, 0. So this distance is x for us. What we have to do, we have only one formula at our disposal. We cannot take it in one shot. We are aware of the only formula which is there with us is Coulomb's law. Coulomb's law, if I am to apply, I need to qualify the application. Qualifying the application means I'll have to cut this line charge into shards, small pieces. Only when it goes to a dimension as small as a point, we are qualified to use Coulomb's law. So in order to supplement whatever there is on board, whatever I've drawn on board, and use Coulomb's law, I'll have to cut it into shards. That is why I'm smothering it. Okay, dear, it being checkered. The line charge being checkered, and I take one such very small length. I'm marking this length dy. It is taken at distance y. What charge will it entail is an obvious. It will entail a charge dq, and dq is what to us? Lambda into dy, where lambda is linear charge density. What we then do, we calculate field due to this charge, and this point to you, right dear?
Yes.
So we calculate field. For field, what we have to do, it's an obvious. Is the direction of field that you'll be getting over there. Because test charge is always positive. I've indicated already about test charge being positive. We take it positive in general, unless stated otherwise. So what do we do over here? This angle theta, this angle 2 is theta. This will be dE vector, mind you. dE vector is in this direction, fine. dE vector. We break it into x and y. This will be dx for me. And the other one will be dy. Analytically, you may say that for every point above will be a counter below which axis? X-axis. Therefore, dEy will sum up to 0. Do you subscribe to this idea?
Yes.
I'm ideating that dy when you sum over entire of the wire, assuming y to be infinitely long, dy will sum up to 0. So what we do, we shift our focus to what we'll be getting of this dispensation. We will be getting only dEx. dEx will keep on adding for every point. What am I to do over here? Though we can, whatever I have said, it can be shown mathematically as well. You take dy, you integrate, you'll get 0. But applying logic, I'm not going for dy, I'm going straight for dEx. And what will be dEx from here? dEx will be dE into cos of the angle theta, right? Yeah. d into cos of the angle theta. What about d? Use the formula 1 by 4 pi epsilon naught charge. What charge? Lambda dy. This is the charge. 1 by 4 pi epsilon. And what distance we do have? This is x, this is y. So x squared plus y squared raised to the power half, and then what we have to do? We have to square it, correct? For field, we'll have to square it, correct? Correct, Vibhan?
Yes, sir.
So half I have taken for distance and squared it. I'm getting that quantity out there. This should be multiplied with cos theta. What shall I write for cos theta? We look into the figure which is indicative of right angle triangle. And what will be cos theta? Base by hypotenuse, correct? Yeah.
Yes.
Base is what to us? X to us, and hypotenuse yet again x square plus y square. This time under root retains. We get from here lambda 4 pi epsilon naught x dy divided by x square plus y square raised to the power 3 by 2. Okay? 3 by 2. 1 plus 1 by 2, right? So 3 by 2 is what we are getting here. What next? What shall we do next?
So
We have to go for integration. Of course, we'll have to go for integration. But before going for integration, there are two variables. One is constant over here. So please don't be of the idea that x is a variable. We are not varying x. X is a constant over here. Point is fixed. The only variable being y. You can go for integration and you will integrate y from where to where? From minus infinity to plus infinity, right? Or if you want to do by angle, which is of course the better methodology, then what you'll have to do is what I'm emphasizing now. Y from here, if you look into this, y from here is nothing but x tan theta. Do check class. Tan theta is y by x, correct? So y is equal to x tan theta. Dy will be how much for us? X sec square theta d theta, okay?
yes.
What we can do, lambda as it is, 4 pi epsilon naught as it is, x as it is, dy is x tan theta divided by now x square as it is.
So I think
Y
you made a
what
mistake
to
in
it?
the substitution.
Yeah, I am taking, I told you that
The
you can
dy
go with y or you
The
can
dy
go
is
with x.
The dy is not x
Yes,
tan.
dear.
Dy is not x tan theta.
It's not x tan theta?
So it's
Tan
x.
theta is y by x, right? Yeah.
Yes, but you substituted x tan theta in place of dy. It should be x secant square theta d theta.
Acha, okay, here. X sec square theta. So this should be dy sec square theta d theta. Okay, now what we do? We'll take lambda 4 pi epsilon naught And tell me what are we getting over here? 1 plus sec square theta, 1 plus tan square theta, right? This will be squared as well. 1 plus tan square theta, we can take x cube outside. X square we have in numerator. This will be x cube. And 1 plus tan square theta. Sec square theta, right?
So secant cube theta.
So we'll get sec cube theta over here, which will go up thereby cos theta d theta, right? Okay. You check.
So wasn't it? Shouldn't it be cos cube theta?
It's square.
Oh, okay. Cancels. Yeah, sure.
I'm cancelling it out.
Yes, sir.
Okay. So that's what we are getting. Now from here, lambda divided by 4 pi epsilon naught x and sine of the angle theta, you know from where to where you are to integrate it. Please do check class.
Yes, minus 90 to plus 90.
Yeah, minus 90 when you look down it is minus pi by 2, when you look up it is plus pi by 2. So pi by 2 minus minus plus pi by 2 will get you 2 there, correct?
Yes, sir.
Eventuating it to lambda divided by 2 pi epsilon naught x. Remember this value is very important. You are having only ex. You are having only ex and it is equal to lambda divided by 2 pi epsilon naught x. This being the case when we have taken infinitely long thread. What if it is semi-infinite, a concept which in mathematics is divorce of sense, but in physics we do use. In mathematics there is nothing infinity by 2, but in physics we do use and it's very logical. If one it is visible, the other is not. One it is straight up front, the other is not. We treat it to be semi-infinite. Everything will remain, only change. Integration will have the upper limit and the lower limit. One of the two changed. Which will be changed? Will let me know, Vibha. Which limit will change? One is straight up front. So which limit will change? Lower limit instead of minus of pi by 2 will be 0 now, correct?
I didn't get the semi-infinite thing. I didn't understand
Semi-infinite means this is absent. Okay. So this time we'll be integrating with the lower limit 0 and upper limit pi by 2. This for EY. Here, this for EX. Here, EY will also be present. And for that, why will EY be present is an obvious. Do the mathematics, you will get to know that EY will also be present. When you do the mathematics, only this factor will change. This will change to sine. And this will change to cos. So that will make you understand that in this case, in the case of semi-infinite, EY will also be present and will be same as EX. What will be EY? Lambda divided by 4 pi epsilon naught x. EY will be lambda divided by 4 pi epsilon naught x, and so will be EX, lambda divided by 4 pi epsilon naught x. Resultant, of course, will make what angle known to you? 45 degree. And what will it be? EX square plus EY square under the root, right dear? EX square plus EY square under the root. Am I clear on that front? Viva, is it clear?
So what is EY? That E.
I said EY will be same as EX. EY means you will have Y now. There is no counterpart. There is no counterpart. Here EY will also be present. Here EY was not present because up and down they were cancelling each other. But in semi-infinite, EY and EX both are to be present and they will have the same value, which is lambda divided by 4 pi epsilon naught x.
Yes, sir.
Okay?
Yes, sir.
Okay. Now before we go for the other configuration, it is important for us to throw some light on potential. What is potential? The other physical quantity. What is potential? What do we mean by potential? For that, what we do, write down, let us take a charge capital Q. Let us take a charge capital Q fixed to the frame shown in the figure. Fixed to the frame shown in the figure. And bring a charge small q and bring a charge small q from infinity to point P. Bring a charge small q from infinity to point P. So this is a charge q which I'm moving from infinity, bringing it closer to capital Q. Capital Q is glued, capital Q is fixed. Capital Q cannot change, small q I'm bringing from infinity. And please be very careful because steps are jumped here. I'll be taking in watts and all in toto, every step with clarity. Please be very mindful of what I'm writing for mod here. Okay, threadbare. Whatever being written will be threadbare. Let's try to figure it out. Let's try to see it in all possible detail. What I'm trying to calculate is work done by me or work done by field force. Which force? Field force. By field force, what I mean? Force on small q due to capital Q. Yeah? Force on small q due to capital Q. That is the field force. So I'm trying to calculate work done by field force. FF dot dr is what I write. Very simply. Work done by field force is FF dot dr. And remember the best definition for potential energy. I repeat, the best definition for potential energy is negative of work done by field force. That is the definition for potential energy. Don't ever go by work done by applied force. You may fall in trap. Okay, situation may go topsy-turvy the moment I introduce another field or I start moving with certain speed. Then that will not be the correct calculation. But you will never fail, you will never be in ruse if you are going by negative of work done by field force. Okay, never be in use. Negative of work done by field force. So whenever potential is still defined, what do we define it as? Potential energy is nothing but negative of work done by field force. Having said that, let us further it. Negative means what I have to do, mod of FF, mod of dr into cos of the angle between FF and dr. I'm writing theta for now. Now mod of FF, I take any arbitrary position. Look over here. I'm taking any arbitrary position. What is the distance? Let's say small r. So what will be FF there? Field force is an obvious. Field force will be 1 by 4 pi epsilon naught. Capital Q, small q, right? By r square, right? Yeah, do check.
Yes,
1 by 4 pi epsilon naught, capital Q, small q by r square. There is a force between the charges over here, right?
Yes,
Mutual
sir.
force. Okay. And that being positive, I have taken capital Q, small q to be positive, so I don't have any comps removing mod here. Then comes the factor mod of dr. Please be careful that when you write mod of dr, basically you're writing dx square plus dy square plus dz square whole under the root. Now over here, these don't merit. So what will it reduce to is dx square under root. Mathematics says this is mod of dx. Clear? Now you have to check. As you are moving from where to where? Infinity to this point, what is happening to x? Or over here, what is happening to r? Of course, r is decreasing, correct? Yeah.
yes.
Yes, sir.
As r is decreasing, mod of dr, which is mod of dx, will be positive if I have to remove mod. I mark mod. I know what will mod be. Are you getting it? I can mark, I can take one more step if you want, mod of dx, okay. This can be r, and then the angle, I'll come to angle later. After this, minus 1 by 4 pi epsilon naught, capital Q, small q by r square, okay. Now mod of dx, what is happening to dx known to you, or what is happening to dr known to you? So what we can do, we know that r is decreasing, therefore what should we write? If I am to remove mod, what shall we write? We should write minus of dr, yes or no? Think about it.
Yes.
Yes or no? Vibha, minus of dr. Why minus? Because dr per se is negative. How is dr negative?
Yes,
Dr
it's
means
between-
final minus initial. dr means final minus initial. Change means final minus initial. And final r, as you are coming closer, will be lesser than initial r. Correct, dear?
Yes, sir, it'll decrease.
So mod of dr, when you want to remove mod, you will have to introduce a negative sign to make it positive. Then coming back to force. Force on this is to the right and it is getting displaced to the left. dr means over here. Let me show dr. This is dr. dr to the left. Correct, yeah? Force to the right and dr to left. Displacement to left. Clear?
Yes, sir.
So what is the angle between force and dr? Force and dr angle will be pi. Cos pi. What will be cos pi? -1. Getting it?
Yes.
Which will get me from here minus, 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 and this one square, another minus, correct? So minus of 1 by r will be integration, yes or no? Integration of r square will be minus of 1 by r, correct?
Yes, sir.
So we get from here capital Q small q divided by 4 pi epsilon naught in the bracket 1 by r. Now you can take the limit from where to where? R infinity to Rx. Okay. R infinity to Rx. Yes or no?
Yes, sir.
We have to bring it over here, right? Point P. What do we get to see then? Capital Q small q divided by 4 pi epsilon naught x. This is the potential equation. Potential energy at P when the reference is taken at infinity. Potential energy at P when reference is taken at infinity. Potential energy per unit charge. That means if I am removing small q by test charge, then when I calculate potential energy, that will be given a special epithet, and that will not be potential energy, rather will be potential. Why? Because small q will lose its relevance. It will be all about capital Q. Mind you, when you are talking of U, when you're talking of potential energy, it's a phenomena which relates to system. Potential energy cannot be studied in isolation. So it is a relative quantity and it relates to system. There should be interacting bodies. But potential can be studied as alona. Okay, dear? So potential is subject to a particular, potential energy is subject to system. Am I clear on this aspect? The moment you change Q to test charge will not partake, and then you are referring only to capital Q. Therefore, potential is nothing but U by Q. We have a symbol for it, V, and what do that bring? Read from here, capital Q divided by 4 pi epsilon naught x. Here you can say that capital Q can stake claim to it. Capital Q cannot stake claim to U. But capital Q can stake claim to V. What is V called? V is called potential. And U is what to us? Potential energy. This also is a simple diagrammatic representation. If you want, you can plot for it. Right here. Key to the plotting, you keep nothing much. Is akin to, I would say, field. But field changes at a faster rate as there is x square in denominator than this. So this being potential. Now, we will not be calculating for every configuration potential. Why? Because we have a relation between potential and electric field. We have a very simple relation between potential and electric field, which comes from where? Comes from where? This comes from where? Now du is what to us? We write it down. What is Fe or Ff as I marked over here? Minus of QE, can we write it down? QE dot dr, do check class. Okay, instead of FF, we had studied the other day, force can be marked as Q into E, right here? So QE, now what we do? Du by Q will get me dV, very important relation in this class, is equal to E dot dr. I'll dwell on this relation for a few minutes. Very important relation this. dV is equal to minus of E dot dr. Please don't make light of this relation. It's very important for us. dV is equal to minus of E dot dr. This relation will fetch us one from the other. If I calculate potential anywhere, I'll get field by uses of this equation. If I calculate field, we'll get potential by uses of the same. Now, what is so important about this equation? dV is equal to, I express it now as Ex dx plus Ey dy plus Ez dz. Do check. Okay, simply writing E as Ex I cap plus Ey j cap plus Ez k cap and dr as dx I cap plus dy j cap plus dz k cap. Write it down, Viva. Ex as Ex I cap plus Ey j cap plus Ez k cap. We can write E as Ex I cap plus Ey j cap plus Ez k cap, and we can write accordingly dr as dx I cap plus dy j cap plus dz k cap. If I'll find E dot dr by uses of Ax bx plus Ay by plus Az bz, we got this, correct? From here, what we can write for Ex? Ex solo is partial derivative of V with respect to X. Similar interpretation go for Ey and Ez. Partial with respect to Z. We wish to write value of E now. E is what to us? E vector. Known to you. I write Ex as minus of this I cap minus of this one j cap minus, we also say dou but doesn't sound good, the partial derivative of V with respect to X. Alright, dear? Now what is this? This factor. This factor can also be marked as d dx I cap plus d dy j cap plus d dz k cap, and can place V outside. We can place V outside.
It doesn't seem
This is
very
basically an
mathematical.
operator, nothing much. If I give it separately, it's an operator. It operates on a scalar quantity to get you a vector quantity. As this is a symbol for operator, this is a symbol for operator, this is a symbol for operator, this is a symbol for operator. So for this operator, we have a symbol. What is that? There is a name for these symbols. For this operator also there is a name. It is called gradient, or in short, grad. It is called gradient, or in short, grad. How do we then write it down? Gradient of V. E is what to us? Gradient of V. This is how we get to write it down in an appealing, what appears to us appealing in that form, but we need to understand what is this inverted triangle with a bar on it to be understood. What it is to be understood. And to get better understanding on it, I give you a question from Iredo. Write down. Given V is equal to XYZ, find Ex, Ey, Ez at 1, 2, 3. Find Ex, Ey, Ez at 1, 2, 3. Ex, Ey, Ez at 1, 2, 3. Pretty simple, we'll be able to figure it out, right? We are just to partially differentiate. If you are partially differentiating for X, then Y and Z are to be constant. Please be mindful of the minus sign here. What do we get? Minus YG I cap, correct here? Then minus XG J cap and minus XY K cap, correct?
Yes, sir. -6, -3, -2.
Yeah, we'll place the value and accordingly we'll be getting whatever or whichever point it being asked at. Sometimes it is sugar coated, I would say, or camouflage. Taking again a question from Iridove, they got you U or V is equal to K by R. And they told you that R is a position vector. They are asking you to find Ex, Ey, Ez. K by R, K is a constant. So I would say it is being obfuscated. Why is being obfuscated? I didn't get X, Y, Z there. I didn't get it directly. We'll have to decode it. What will be R represented by? X square plus Y square plus Z square under the root, correct? R is a position vector and R is magnitude wise given to you. So R can be replaced by X square plus Y square plus Z square under root, and then you can go for partial differentiation to get Ex, Ey, Ez. Correct, dear? Yeah.
So couldn't you just treat R like one dimension, because this clearly has spherical symmetry smeared all over it.
But you won't get Ex, Ey, Ez, right, dear?
Yes, no,
Of
I mean, you can get it in one dimension and then you can just like turn it on.
We can take it in R. Of course, we'll be doing the same. We'll be taking it in R and then we'll be breaking into components. That also can be done. Okay, then we move on to the other factor wherein, I don't know how many pages you must have used in order to figure it out. We'll be trying to do it in the most amicable manner. And what that being, I have to find electric field due to a dipole. Dipole means equal and opposite charges, point charges separated by certain distance. We'll be doing it in 3 steps, not more than that. Equal and opposite charges separated by very small distance. So the analogy is either the charges are separated by small distance and the point where you want to calculate field is significant. I'm repeating. Either the point charges are separated by very small distance and point you want to calculate electric field at is at a significant distance from the point charges, or charges are separated by significant distance and point that you have taken for calculation is at infinity.
So how are the 2 cases exactly different? I mean,
it's exactly the same, dear. It's exactly the same. This is the case near to you. Going far, it'll appear to you that they are coming closer.
It just seems like a difference in perspective.
Analogy, yeah. The analogy is the angle that is subtending to your eye. What will appear to you? You will observe the height or the differential by what is being subtended to your eye. And subtended to your eye will certainly be less when you're going far, remote from it. So the analogy is, I repeat, either the charges are actually at insignificant distance located from each other, insignificant distant, and the point where we are calculating their effect is at significant distance from these charges. Or the charges are at significant distance and the point that we are calculating the effect will be at infinity. Okay, they're analytical. So what I do, I take quickly the case at hand. This equation I'll be using later here, dV is equal to minus of E dot dr. In fact, the other 2 attribute of line charge, we have taken line charge attribute. That can be not line charge. We have taken attribute of field force, line field force. I told you when we were defining potential, we'll be reading about it. So that can be justified by this equation. I'll be coming to it. No hurries. Okay, over here we have taken capital small q and this is minus. I want to find field over here. Yeah, this point. This is R1, this is R2. And my point is very far. My point being remote, a far cry to reach there. What do? I know that these lines which are appearing to me forming a triangle will never form a triangle. Why? Because the point where I'm trying to calculate is at infinite distance, which makes these 2 lines parallel to each other. Say me yes or no?
Yes, sir.
Parallel lines are to meet at infinity. So these are actually parallel lines to you. Assume that to be parallel lines and tell me if I am to calculate distance between parallel lines, differential on distance between parallel lines, length differential, then what I do? From the shorter one, I will draw perpendicular to the longer one. This will be the differential, correct? Yeah. That is the methodology. If I am to find differential between the lengths, correct? Yeah.
Yes, sir.
So there are two lines over here. They are parallel. That is what we have to assume. Implied they being parallel, I draw a perpendicular. So this will be what to me? This will be R2 minus R1. This distance.
Sir, I have a little doubt
R2
here.
minus R1. Yes, dear.
So your choice of which line would be parallel to which seems kind of arbitrary here. I mean,
QP minus QP, they are parallel. Why so? I have taken distance significant and point at infinity. These lines are meeting at infinity. They ought to be parallel, right? Yeah.
yes, and that's, but like at infinity, either P can keep going along P minus Q, or P can keep going along PQ.
I'm taking angle the same. I'm not changing the angle. I'm not changing the angle. Yeah. If this is theta with horizontal, this too is theta with horizontal. This too is theta with horizontal. Okay, they are all theta. Yeah.
Okay.
They are all theta. We can mark this one as small r. OP small r, QP is R1 minus QP is R2. Fine?
Yes, sir.
Okay?
Yes, sir.
And then I'm trying to find what is the differential between the two. So I'm dropping from one to the other, from one line. This is the line, this is the other line. They are meeting at infinity is what I've shown over here. So this I'm dropping from the end of one, a perpendicular on the other to get the differential. That's exactly what I've done over here. Clear?
Yes, sir.
I calculate potential at that point due to plus Q. What do I get? K Q by R1, correct?
Yes, sir.
Exclusively. And then potential due to minus Q. What do I get? Minus K Q by R2. Exclusively. Total potential will be plus Q plus minus Q. So what do I get? K Q bracket open 1 by R1 minus 1 by R2. This is what to us? KQ R2 minus R1 R2 into R1. Right? Do check here.
Yes, sir.
Now what is R2 minus R1? This factor is R2 minus R1, correct? This theta, if you want to take this 90 minus theta, you can take. Generally they present it in alpha, so I'm presenting in alpha. Okay, tell me what will be R2 minus R1. This is D to me, small d. This total distance is small d. Can we write R2 minus R1 as D cos alpha? Can we write R2 minus R1 as D cos alpha? Do you check the triangle? What does that get from here? KQ as it is D cos of the angle alpha done divided by now R1 into R2. The R1 is slightly greater than this, I say R1. R1 is smaller, or R is slightly greater than R1, and R2 is slightly greater than R. I repeat, R is slightly greater than R1, you may mark, and R2 is slightly greater than R. So what we can do, we can write R1 as R minus delta R, and we can write R2 as R plus delta R. Okay, dear? That'll get me R square minus delta R square, correct?
Yes, sir.
R1 minus delta R, R1 plus delta R, so A minus B, A plus B, R square minus delta R square, which we can simply mark ignoring delta R square as R square.
So, but delta R square seems to be pretty significant here.
Insignificant. That is the reason we have ignored it.
So it seems to be significant because, like, if you
In comparison to R, it will not be.
oh, like R is infinite.
Comparison to R, there is R as well. Okay.
Yes.
So what do we get from here? A Q d cos t or d cos alpha as it is divided by what shall we write? R1 into R2. Tell me now. R square. Agreed? You check please.
Order square. Yes, sir.
Okay. We get from here two variables. Please do check the parameters. There are two parameters that potential is governed by. One is alpha, the other is small r, correct?
Yes,
There
sir.
are two parameters potential is governed by. One is alpha and the other r. And going by our understanding then, we will get ER and we will get E alpha. Alpha. We'll get ER and we'll get E alpha. ER will be simply partial derivative of V with respect to R, but E alpha will be minus of 1 by R, partial derivative of V with respect to theta. Ask yourself why. Why is E alpha minus of 1 by R, partial derivative of V with respect to alpha? Why so? Why not I have used 1 by R here as well? What was the reason it being used exclusively in alpha? Nevertheless, think about it. ER we can get, E alpha we can get, and accordingly we will get equation for field. When you're finding ER, you have to treat alpha constant. When you're finding E alpha, you have to treat R constant. Am I clear, class? You can differentiate and you can get the direction as well. ER means in this direction, this will be ER, direction for ER, and E alpha will be in this direction, this will be the direction for E alpha. Okay? Okay? So we got to know just in 3 steps. Even if you forget in examination hall, what is the value, you can easily calculate from here. I have used over here Young's double slit methodology. In Young's double slit, we do this. We are using over here YDSC methodology to get electric field and potential due to another discrete combination or formation, and that being dipole. Clear, dear?
So could you explain how you got the expression for E alpha again? And whatever.
Which one? This one? This one?
Yeah.
And this one is because when you differentiate, you have to differentiate by length. If you want to write volume, or if you want to write field equation, if I'm to write dV, I'll have to write E dot dr. dr. D alpha doesn't get you. D alpha doesn't get you a dimension in length. What will get you dimension in length? When you are into spherical coordinate or when you're into cylindrical coordinate. You
So
want to take volume, so you have to take arc, correct?
RD alpha kind of gets you that little perpendicular.
Yes, RD alpha will get you the length. Okay?
Yes, I get it.
That's the reason we are dividing it by RD alpha. RD alpha is the length, and accordingly we get the equation for this. Spherical coordinate frame, cylindrical coordinate frame. Spherical will be better understanding. If a spherical coordinate frame is known to you, how do we get sphere? What do we do there? We take r, theta, phi, and in cylindrical coordinate we take r, phi, and z. When you increase them slightly, you get the configuration. That's the reason they are named so. For example, x, y, z, Cartesian coordinate, dx, dy, dz. When you do, then you get small cube. Similarly, dr, rd alpha will be arc, and then dz when you take, then you get cylinder. Dr, okay, this is dr, small arc, small dr, arc is how much? This arc will be rd alpha, this will be small dr and small z. Small z, right? This will get us cylinder. So r phi z or r theta z are the coordinate in cylindrical coordinate. And in spherical coordinate it is r theta phi. Dr you do, then you take arc and you take another arc this way. You get shape of a sphere. Okay, dear. Nevertheless, over here we were to take length, so we are divided by length, length being RD alpha, and accordingly we got E alpha as 1 by R dV by d alpha. We'll be able to calculate it, right?
Yes.
Okay. So this is about potential though. Electric dipole doesn't get over here. We have to study about it being placed in field, then torque experienced by these are to come. We'll be checking them later. For now, what we can do, we can simply calculate for potential and field, which is what we have done. And we can further it to other configuration. The other configuration which I want to take quickly is ring. Write down. Let us take a ring. Let us take a ring with linear charge density lambda. Let us take a ring with linear charge density lambda. Let me remind you, we are not done with dipole. We'll be returning. There are other parameters. There are torque, energy relation, which we have to study vis-a-vis dipole. For now, I have only initiated A, potential, B, field due to it. Find here? Okay. So a ring, and what did I say? Lambda being the linear charge density, radius r. Find potential and field on the axial point. Find potential and field on the axial point. What will be equation for potential and field on the axial point, and then we'll go to disk. I've got a question for you for disk. Just drawing so that I don't lose on it. This is a ring to me. This is X, this Y, and this Z. It's a right hand frame, X, Y, Z. Right hand frame is what I've taken. I'm sticking to right hand frame. And to calculate field, where? Here. What is this distance? X. So this time I'll go the other way. I'll go by reverse logic. I'll calculate potential first. Okay. And for potential, you know, again, I'll fall back to only one term, which is what is known to us, point charges. I'll have to cut it into small pieces. I have to checker the ring and take one such particle. I'm taking one such particle over here. Anywhere you can take on the periphery, dq. dq will be at what distance is an obvious. If the radius is r, which is what I made you write. So r square plus x square under the root. We calculate a small potential that will generate dv. dv will be how much for us? 1 by 4 pi epsilon naught. dq is nothing but dq I have to write for now. Divided by r square plus x square under the root. You know r is constant, you know x is also constant, so v will be nothing but integration on dq, correct? R is constant, x2 is constant, so when I have to integrate to get v, v will be nothing but 1 by 4 pi epsilon naught total charge q divided by r square plus x square under the root. This is what to be, this is v forming. We are next to calculate Ex. Ey will be 0, there is no y factor over here. Ez will be 0, there is no z factor over here. So Ex, which we can write organically as partial derivative of v with respect to x, will actually change to complete derivative of v with respect to x. Total derivative of v with respect to x. When you differentiate, what you have to get from here is an obvious ux divided by 4 pi epsilon naught r square plus x square raised to the power 3 by 2. Okay, I wish I get plot for it. Can I get plot for field? Potential is simple, you'll be able to plot. Can I get plot for field versus x? This field, plot for field versus this total field, by the way. You can say Ex or E, totally on any axial point, which are distance x from the center of ring. What we feel vis-a-vis plotting? What do we do? Any idea, dear? Vasudev, any idea?
I would head to Desmos.
See, we'll get some idea vis-a-vis x placement. That is what we do. In order to begin with, what we do, we take the extrema, x0, x infinity.
Because the
What is the
differentiated
problem? X0 you take, you are getting 0. X infinity you take tending to infinity, then also you are getting 0.
Yes, sir.
Then we'll have to resort to another principle, and that being maximum minimum. We have to differentiate it and equate to 0. When you differentiate equate to 0, you'll get two values of x, plus and minus r by root 2. Plus and minus r by root 2. Two values you'll be getting. This is being taken or not, Vasudev, in class?
Yes, sir. I've done this independently.
Plus
Yes.
r by root 2 will get you maxima. Minus r by root 2 will get you minimum.
Yes.
Okay. Many a time question being asked. Simple harmonic motion execution that is possible provided capital R is very large in comparison to x. Then it becomes proportional to x and opposite in nature. But then another question can be asked, up to what value of x is possible simple harmonic motion? Up to what value of x is possible simple harmonic motion? Think about it. If at all is possible, up to what value of x is possible simple harmonic motion? Not for all value of x simple harmonic motion will be possible. Even if r is taken very large. Even if r is taken very large. Okay, dear? Okay, so this was about ring, correct? We got potential, we got field. Now to disk. Write down, find potential, and this will bring to what you were asking, Vasudev. Find potential and field due to a disk of radius r. Find potential and field due to disk of radius r on its axial point. On its axial point. You can preempt what I'll be doing, isn't it? You can pretty easily preempt what I'll be doing. I'll be cutting the disk into several rings. I've taken one ring of radius small r and thickness dr. Okay, dear? What we charge on this ring? For the first time, we are using surface charge density. So sigma 2 pi r dr. 2 pi r and dr thickness. Sigma is surface charge density. Sigma 2 pi r dr. And then what we have to calculate small potential that will generate. Potential that will generate is an obvious 1 by 4 pi epsilon naught. Sigma 2 pi r dr divided by what we do, r square plus x square under the root. Do check class. X is same, point remains. R has got changed, small r. Capital R is the radius of disk. Okay, what next? What shall we do? We have to integrate. Make good your integration. How? Take z square, another variable as r square plus x square. Shall we? Whichever way you do, that is your prerogative. 2r dr plus 0. 2 into gone. What do we get then? 1 by 4 pi epsilon naught. Sigma 2 pi as it is. R dr change to gz divided by what do we have? Media. Z, is it?
Yes.
Okay. And then integration. Integration from where to where? Please be mindful of you have changed. You have changed the variable. So when r is 0, z will be x. When r is 0, z will be x. When r is capital R, z will be r square plus x square under root. Okay, dear? We get from here 1 by 4 pi epsilon naught, 2 pi as it is, z when you integrate from where to where? R0. So x to r square plus x square under the root. Sigma as well. What eventuating to? Sigma divided by twice epsilon naught bracket open 1 by r square plus x square under root minus 1 by x z. You check please if I missed anywhere. No, it will be up, not down.
So could you write it someplace else?
Yeah.
Not exactly
Sure.
see it on the.
Just a minute. Okay. Potential is what we were calculating, right here. The potential over here we have dz we have taken. From here we are getting z, right?
Yes, sir.
You check. Done.
Yes, sir.
I'm writing over here again. Sigma divided by get again pi epsilon naught, right? Bracket open. What was it? R square plus x square under root minus.
X.
Tell me.
X.
Minus
X.
This potential equation. What about field?
You're aware of it. E, which will be equal to Ex, will be nothing but partial derivative of B with respect to Z. Tell me what will you be getting there? Sigma divided by twice epsilon naught will remain, bracket open, correct? Minus I am taking outside, no issues because there is a minus out here. Differentiation will get me 1 by 2 under root of R square plus X square and then into 2x. And this will be minus of 1. Do check.
Yes, sir.
Or then sigma divided by twice epsilon naught, bracket open. What do we get? Minus taken in. 1 minus, what do we do? X divided by R square plus X square under the root. Please do check. This field equation, correct? And if capital R is very large, if you have got infinitely spread sheet, then reduce to sigma divided by twice epsilon naught, correct? Yeah. Either the sheet is infinite or you are very close to it. Again, analogy. If you are very close, you will not be able to see the edges, correct?
Yes, sir.
Either x is tending to 0 or r is tending to infinity. What do we get to see? Sigma divided by twice epsilon naught. Sigma divided by twice epsilon naught. That is what we are going to get the field as. So this was for sheet. We have taken it for sheet, right dear? And Vasudev, let me tell you, sigma divided by twice epsilon naught, which we have written over here, which is field by the way, will be the field in front of any sheet. So even if you have taken a conductor and you are very close to that conductor, let us say I have taken a 3-dimensional structure. I am very close to it. Will prove that field outside will be nothing but sigma divided by twice epsilon naught. Field outside will be nothing but sigma divided by twice epsilon naught. And then I'll ask you, what if I puncture it? Okay. From there, we'll get to know what is the genesis of pressure. Because after of that, we will discuss what is work done in expanding it and where is this work stored. What is half epsilon naught E square? You'll get energy density and you'll be surprised to know that half epsilon E square, which I'm talking about, is energy density equation, it is stress equation, and it is also pressure equation. They will all be same. And that will eventuate to sigma square by twice epsilon naught as pressure. First thing first, as I said, that I'll be asking a question. So I take a conductor, write down. Let us take an irregular shaped conductor as shown. Again, this you will not be getting anywhere, so please be very careful because they use a different methodology. And that methodology will not reveal on what will happen when you're puncturing it, or will not be revealing how the genesis is being built for pressure derivation. I'm trying to build a genesis. Okay, so what is, we have taken an irregular shaped conductor, find electric field at point P shown in the figure. Find electric field at point P shown in the figure. So I have taken an irregular shaped conductor. You can take of any shape. This is the irregular shaped conductor. This is the point P where I want to find field. Sigma will not be uniform, isn't it? Charge Q, we have standard charge Q, but sigma will keep on changing. Tell me why will sigma change? Sigma depends on radius of curvature. If there is only one radius which you can associate with figure, then sigma will remain, will be uniform. If there are different radii, then sigma will keep on changing. So sigma over here will be subject to position. Correct, dear?
Yes.
Different position will identify with different radius of curvature, and accordingly sigma will change. Correct?
Yes, sir.
So whatever be the case, I am taking a small, very small area over here. And what is the area dimension? Delta S or ds. What is the sigma on it? Is sigma. Okay? That point, for that point, it's almost a point. Sigma is fixed. Very small area. Sigma is fixed. I take one more point inside of it, and that is P prime. Now, E at P, please be very careful, class, as I've told you not be getting. E at P will be E at P due to delta S plus E at P due to rest of the structure. Agree? Similarly, E at P prime will be E at P prime due to delta S plus E at P prime due to rest of the structure. Due to rest of the structure. Get here? P prime is inside of the conductor, right here? So field 0, agree? What do we get from here? E at P prime due to delta S plus E at P prime due to rest of the structure will equate to 0, correct? We know E at P prime due to delta S, just now we read. You are very close, so it is infinite, correct? Yeah.
Yes, sir.
We can write sigma by twice epsilon naught, and I am taking eta vector outside, so eta, unit vector outside. What will be? Minus of eta then, do check class. P prime,
Yes.
correct? Sigma twice epsilon naught, which direction? Because I have eta I have taken outside, okay dear?
Yes.
Plus E at P prime due to rest of the structure. What do we then get? E at P prime due to rest of the structure is equal to how much? Sigma by twice epsilon naught into eta. It goes to this side, eta. Now I come to this one. Not P prime, but P. I wanted to find E at P. So I rewrite E at P. What is that? Firstly, it is E at P due to delta S, correct?
Yes, sir.
What will it be? Sigma divided by twice epsilon naught eta due to delta S. And then E at P due to rest. E at P due to rest is how much, dear? Will be equal to E at P prime due to rest. Tell me why. E at P due to rest will be equal to E at P prime due to rest because delta S is the only distinction. If you remove delta S for rest of the structure, P prime and P are same. Getting it? So for rest of the structure, what we can say, E at P prime produced by rest of the structure will equate to E at P produced by rest of the structure. Clear, dear?
Yes, sir.
What do we then get from here? Sigma divided by twice epsilon naught into eta. Adding them, we get sigma by epsilon naught into eta. Do check class.
Yes, sir.
This is the field. This will be the field which you will be getting over there. It goes without saying, tell me. In fact, let me ask you. If it is being punctured, then what will happen to field? If I puncture means what I am doing? I am moving this part. Field will reduce to half, very important. The moment you puncture, even a cyclist, a head of pin, if you are going by, it punctures hole, it will get the field reduced by half.
So
Delta S
everywhere on the
part will be a
surface?
miss, correct? Delta S part will be a miss, correct?
Yes, sir.
Because delta S you have removed. What will happen to field? It will reduce to half. Yes, Vasudev, you are asking something.
So when you said reduced to half, where? Around that localized point or everywhere?
Here. I'm calculating here only, right?
Yes, sir.
Reduce to half. The moment you're just puncturing, it will reduce to half at that point. Delta S will not play any role. Okay? Am I clear?
Yes, sir.
Okay. Now on, what is the time? Shell we can take quickly. What's the time?
So 2010.
8:12. 8:12.
We can take it later. Okay. Shell, if you are aware of shell, then at least I can make that point clear to you. What about shell? Okay, and energy density. Write down energy density. Energy per unit area per unit volume. Energy per unit area per unit volume is defined as energy density the stress and pressure can be proved to be sharing this equation. Stress and pressure can be proved to be sharing this equation. Now, just to quickly relate to, because we are running slightly thin on time, just to quickly relate to, this is a sphere, okay, dear, of certain radius. Only field over here at this point, just now we got sigma by epsilon naught radially outward. Agreed? Only field over there? From yes or no?
Yes.
Yes, sir.
If the sphere which we have taken is allowed to expand, you approve of expansion. What happens? Radius increases. Small r was the radius. It has increased by small amount. What that amount? dr. Small it is, I'm magnifying. You'll get eluded by it. dr. Okay. We took a very small area. Delta S. What was the charge on this area? Sigma into delta S. What was the force on this charge? Sigma into delta S multiplied with sigma by epsilon naught. Is it okay? Charge sigma into delta S, force sigma into delta S multiplied with field there. Say me yes or no, Vasudev?
So with the field sigma or epsilon naught, we got that on the point right outside, right? How do we know?
Yeah, right outside only. Dr is very small. Right outside what the field sigma by epsilon naught, right?
So, but that's when like the sphere itself has enlarged to reach that point. So how can we say that's the field on the surface itself? That's
Because we will be proving that it is a continuous function. Okay? Continuity will show it is a continuous function. It will not be differentiable, but it is continuous function. Okay, we'll prove that. It is not differentiable, but it will be continuous function. And if you know the formula, you can yourself prove there. Inside of it, field is 0, outside is field. Yes or no?
yes, sir.
Okay, what is field equation? Q divided by 4 pi epsilon naught small r, right? Small r square, right?
Yes, sir.
Capital R square. Capital R is the radius and capital R square. And inside is 0, right?
Yes, sir. That doesn't look like
So it is not
continuous function.
differentiable. Potential is not differentiable, but potential is continuous.
So don't you have a jump discontinuity right around R, where it jumps from whatever value it has inside?
Because we have not taken that configuration. And we'll take that configuration and then plot for it. Then we'll get to know, right? I'm not taking, I wanted to highlight because you did ask and we began with the premise that we'll be touching that portion. So I'm trying to touch that portion. It's not getting done in this class.
Yes.
Okay. So field multiplied with what I did, multiply with charge. Idea? That is getting me force. This force, again you'll say that will change, but I've taken dr very small. So this force will do what work? This force will do this multiplied with dr work, right? This much work.
Yes, sir.
This work, which amounts to energy, where it is stored? In that volume. Which volume? Look over here. This volume. What is this volume? Delta S into dr, right?
Sir, but don't the particles also gain kinetic energy while expanding?
Come again?
Don't the particles also gain kinetic energy while they're expanding?
No, it's very slow process. We're taking it slow.
Okay.
So this is where the, otherwise I cannot say energy will be stored. Entire of the energy will not be stored there.
Yes.
Some part will be taken by kinetic. It's slowly expanding. We get, and by the way, I'm calculating work done by field force. So it'll anyway be potential, even if it's getting kinetic energy.
Yes, sir.
So work done is that much divided by where the energy is stored. So energy is stored here, right? Why I say so? Previously there was energy in this part, when small r was the radius, there was energy because where is field is energy. But when you expanded and engulfed it, there is no field, no energy. That one energy is lost. So what I'm trying to do, I'm trying to find, okay, energy, work that I'm doing, where is that getting stored? It is getting stored over here. Or what is the energy lost? Here, which force is doing work? I'm stopping it, by the way. Field force is doing work, correct? Whenever field force will do work, what will happen to potential energy? It will decrease. Field force doing work, potential energy decreasing. So field force is doing over here positive work. That's the reason there was potential. Now that potential is lost. Where was potential stored? In this region. So potential energy per unit volume. What does that get me? Sigma square by epsilon naught. Do check here. Sigma square by epsilon naught. Getting it?
Yes, sir.
Okay, we'll be proving that. Not to worry, we'll be proving that. There'll be half factor as well, which will feature later. As I've told you, half epsilon naught E square will be energy density. Half epsilon naught E square is energy density. So we'll get to know how do we get to half epsilon naught E square relation.
So what is the quantity we just calculated now? Sigma square over epsilon naught?
Sigma square, that is also in sigma form. Same term, dear. Half epsilon naught E square in sigma form. In sigma form, electric field you write in sigma form. You can write electric field in sigma form, right?
Yes.
Okay, dear. That's it for the day. I'm keeping to this today. Or maybe, I'm not very sure, but there will be a compensatory class as we have missed on Monday. So there can be a compensatory class tomorrow. And I'm planning the mathematics class. So you please do tell me when can you, after 21st, be comfortable taking mathematics class. First class will be on permutation, combination, and probability. So
Yes,
there will be the guy who will be taking the class at the stipulated time of your convenience. There will be other students also who will be joining from 21st onwards. So you'll be taking a combined class.
Yes, sir.
PNC and probability.
Okay, sir.
Okay, thank you, dear.
Thank you, sir. Good night.
Bye.